Hello everyone, my name is Guojing Zhou. Welcome to my talk. Here's the title, which is about explaining hierarchical reinforcement learning induced pedagogical policies. In this talk, I'm going to show that such explanations can enhance students' engagement on intelligent tutoring system. Intelligent tutoring system is a type of adaptive e-learning environment that can dynamically tailor students' learning experience. ITS typically employs pedagogical policy to decide which action to take when there are multiple ones available. In a typical ITS training cycle, the student interacts with their learning environment and the pedagogical agent takes pedagogical actions to control the interaction between the student and the learning environment. In other words, most existing ITS are tutor-centered in that the tutor decides what the student should do. While a lot of prior research has shown that such training cycle can effectively help students learn, we still face a major challenge about communication there. That is, the tutor rarely explains to the student why the pedagogical decisions are made. On the other hand, prior research in self-determined theory suggests that giving explanations may enhance student engagement. Therefore, we generated explanations for our ITS and investigated our first research question: would explaining the tutor's decisions enhance students' engagement and in turn result in better learning outcomes? In a classroom study, we compared the explanation condition with the baseline condition without explanation. In both conditions, the tutor randomly decides whether to elicit the next step from the student or to tell it to the student directly. However, results show that there was no significant difference on learning performance and engagement between the two conditions. One possible reason is that randomly deciding elicit versus tell may not always be effective. In order to create effective instructional interventions, we then applied reinforcement learning to induce pedagogical policies. In recent years, as many of you may know, reinforcement learning is becoming more and more powerful. It has been shown that reinforcement learning can beat human expert players in complicated tasks such as Go and video game. Given all the advances, a lot of prior research applied reinforcement learning to induce pedagogical policies, including some of the works in our lab. In our prior work, we made the first attempt to apply hierarchical reinforcement learning to induce pedagogical policies. Overall, results show that reinforcement learning policies can be effective. Applying reinforcement learning to the ITS training cycle results in human-centered reinforcement learning, which is different from standard reinforcement learning. In standard reinforcement learning, the agent interacts with the environment to learn how to make effective decisions, and the ultimate goal is to make the agent smart. While in human-centered reinforcement learning, the agent takes pedagogical actions to control the interaction between the student and the environment. Here, the ultimate goal is to make student-system interaction productive. Again, motivated by the self-determination theory, we applied a data-driven approach to generate explanations for our HRL-induced pedagogical policy. Then we investigate our second research question: would combining explanations and HRL policy enhance students' engagement and result in better learning outcomes? In another classroom study, we compared the explanation plus HRL condition with the baseline condition, which employed random parser with no explanation. Results show that combining explanations and HRL policy indeed can enhance students' engagement and result in better learning outcomes. Here's the outline of my talk. I will start with the explanation study. As mentioned before, here is the research question. In this study, we generated action-based explanations which specify the benefit of taking a tutorial action based on prior cognitive science research. We wrote the explanations following the principles suggested by Daisy et al. More specifically, the explanations specify the benefit of the action using a non-controlling wording. Here, our ITS makes pedagogical decisions at two levels of granularity. At the problem level, it decides whether the next problem should be work example, problem solving, or collaborative problem solving. While at the step level, it decides whether to elicit or tell the next step. Here are some example explanations. For work example, we explain the AI agent will solve the next problem for you to save your time. Here, saving time is a benefit. Additionally, to create a non-controlling task, we describe what the AI agent will do. Similarly, for collaborative problem solving, we explain the AI agent will solve this problem together with you to improve your learning. Here, improving learning is benefit. In a classroom study, we compared the explanation condition with the baseline condition. The participants were undergraduate computer science students enrolled in the discrete math class, and this study was given to them as one of their regular homework assignments. We focus on two types of measures: learning performance as measured by normalized learning gain, and engagement measured by percentage of correct elicits and hints per elicit. Students were randomly assigned to the two conditions, and this table shows the number of students we assigned to each condition, finished the study, and included in our data analysis. Students who performed perfectly in pretest completed the study in groups or rushed through the pre or post-test were excluded. A chi-square test showed no significant difference in completion rate between the two conditions. All students went through the same four-phase procedure. In pre-training, they read a probability textbook. Then, all students completed a 14-problem pretest with no feedback. During training of practice, all students completed the same 12 problems in the same order. Here, the conditions differ only by the presence of explanations. Finally, all students completed a 20-problem post-test, and 14 of them are isomorphic to the pretest. The pre and post-test were graded following the partial credit rubric, and the scores were normalized to 0 to 100. In order to investigate students' improvement during training, we compared their pre and isomorphic post-test score. A repeated measure analysis showed that both conditions scored significantly higher in the isomorphic post-test than in the pretest. In order to investigate students' learning performance, we analyzed their isomorphic ALG and ALG. Results show that there was no significant difference between the two conditions on these two measures. For time on task, the EXP condition tended to spend less time than the baseline condition. Finally, the results for engagement was kind of unexpected. There was no significant difference between the two conditions on both the percentage of correct elicits and hints per elicit. Overall, the results suggest that explanations alone may not always enhance students' engagement and learning performance. Next, the explanation plus HRL study. Just to remind everyone, here is the research question. In this study, we generated policy-based explanations which give a reason behind the HRL policy's decisions. However, since our HRL policies are represented by complicated models that makes decisions based on 142 features, it's hard to generate the explanations by directly analyzing the policy. Therefore, we generated the explanations via two steps. First, we trained a supervised learning model based on the HRL policy, and then we took the key features of the model as the key features of the HRL policy. Using this method, we identified 4 problem-level features and 3 step-level ones. Then, based on the key features, we wrote explanations. Here are some example explanations. If the feature indicates that the student is working fast and HRL gives a work example, we explain No need to hurry. Please watch closely on how I solve this problem. Similarly, if the picture indicates the students working slow and HRL gives a step-level tell, we explain, to save your time, I'm going to demonstrate the next step. In another cornerstone study, we compared the explanation plus HRL condition with the baseline condition, which employed random policy with no explanation. Again, the participants were undergraduate computer science students. We still focus on two types of measures, learning performance and engagement, and this table shows the number of students we assigned to each condition, finished the study, and included in our data analysis. A chi-square test showed no significant difference in completion rate. A repeated measures analysis showed that both conditions scored significantly higher in the isomorphic post-test than in the pre-test. For learning performance, the EXP plus HRL condition scored significantly higher than the baseline condition in both the isomorphic NLG and ALG. For time on task, there was no significant difference. In terms of engagement, for percentage of correct elicits, the EXP plus HRL condition had a significantly higher percentage than the baseline condition, while for hints per elicits, there was a trend that the EXP plus HRL condition requested less hints than the baseline condition. Overall, the results suggest that explanations and effective pedagogical policy together can significantly enhance both student engagement and learning performance. Next, post-hoc analysis. In order to further examine how the explanations and HRL policy may impact student learning, we conducted a post-hoc analysis that involved the two empirical studies and another one from our prior work. The 2x2 analysis involved presenting versus hiding explanations and HRL versus baseline policy. For learning performance, there was a main effect of pedagogical policy in that the HRL groups scored significantly higher than the baseline groups in both the isomorphic NLG and ALG. Subsequent contrast analysis showed that when there was no explanation, HRL significantly outperformed baseline. The results suggest that HRL policy indeed can improve student learning performance. For time on task, there was a main effect of explanation in that the explanation groups spend less time than the no-explanation groups. In terms of engagement, for percentage of correct elicits, there was a main effect of policy in that the HRL groups had a significantly higher percentage than the baseline groups. Subsequent contrast analysis revealed that EXP plus HRL had a significantly higher percentage than EXP and a marginally significant higher percentage than HRL. For hints per elicit, there was a main effect of explanation in that the explanation groups requested less hints than the no-explanation groups. Contrast analysis revealed that EXP plus HRL requested less hints than HRL. The results suggest that explanations and HRL policy together can enhance student engagement. Conclusions. Summarizing the results, we conclude that explanations alone may not always enhance student engagement and learning outcomes. HRL-induced policies can enhance student learning outcomes, and explanations and HRL policies together can enhance not only student engagement, but also their learning outcomes. That's all for my talk. Thank you.